Nothing in your life has ever been still. Not the chair beneath you, not the floor beneath the chair, not the planet beneath the floor. Right now, at this exact moment, the ground you're standing on is moving at 1,670 kilometers per hour. You do not feel it. You will never feel it, but it is happening. And it has been happening every second of every day since before your species existed. To be confused by it, that is where this story begins. Not with distant galaxies or abstract numbers. It begins here, with you. Because before you can understand how big the observable universe actually is, you first need to confront something far more personal. You have been wrong about where you are your entire life. Let us be precise about the wrongness. Earth rotates once every 24 hours. At the equator, that rotation translates to a surface speed of roughly 1,670 kilometers per hour. You are, in a very real sense, a passenger on a spinning rock. But the rock is also moving. Earth orbits the Sun at approximately 17,000 kilometers per hour. In the time it took you to read that sentence, you traveled roughly 15 kilometers through space. And the Sun is not sitting still either. Our solar system is orbiting the center of the Milky Way galaxy at approximately 828,000 kilometers per hour. One full orbit takes about 225 million years. The last time we were in this exact position in the galaxy, the first dinosaurs were just beginning to walk the Earth. Before that, it was before complex life existed on land at all. But even that is not the full picture. The Milky Way itself is moving. Our entire galaxy, all 100,000 light years of it, is being gravitationally pulled toward a concentration of mass so enormous that astronomers could not ignore it, even though they could not see it. They named it the Great Attractor. It sits roughly 250 million light years away, and it is pulling our galaxy toward it at approximately 600 kilometers per second. Not per hour, per second. Add it all together, spin, orbit, galactic rotation, cosmic drift. You are hurtling through the universe at a combined velocity that no human nervous system was designed to register. Your coffee sits still in its cup. Your phone feels solid in your hand. Everything around you whispers ordinary, but none of it is ordinary, not even slightly. So here is what that means. If you're moving this fast in this many directions simultaneously and you feel absolutely nothing, what else about your position in the cosmos are you getting completely wrong? The answer starts close to home. Earth, a sphere, roughly 12,742 kilometers across at its widest point. If you wanted to drive that distance in a straight line, assuming a highway could somehow run through the planet's molten core, it would take you approximately 5 days at highway speed. Longer if there is traffic. It feels enormous. When you fly across an ocean for 10 hours and look down at the clouds and the endless blue below, the scale of Earth feels genuinely incomprehensible. It is not enormous. Not by any standard that matters. Place Earth next to Jupiter and something shifts inside you. Jupiter's diameter is about 11 times Earth's, but diameter is not the right metric for scale shock. Volume is. Jupiter is 1,321 times the volume of Earth. If you hollowed Jupiter out and started pouring Earths inside, you could fit over 1,000 of them before running out of room. You would still have space left over. Jupiter is so massive that it does not technically orbit the Sun the way you were taught in school. Technically, Jupiter and the Sun orbit a shared gravitational center called the barycenter. For most planets, this barycenter sits well inside the Sun's surface. For Jupiter, it sits roughly 1.07 solar radii from the Sun's center, which means the barycenter is actually above the Sun's surface. Jupiter is so heavy it pulls the Sun into a slight wobble. Jupiter does not orbit the Sun. Jupiter and the Sun orbit each other, a planet that bullies its own star. And yet, the Sun contains 99.86% of all the mass in our solar system. You could fit approximately 1.3 million Earths inside it. Jupiter, enormous as it is, barely registers. The Sun is not even large by stellar standards. It is classified as a G-type main sequence star. In astronomer language, that means average, ordinary, unremarkable. So what does a remarkable star look like? In 2012, astronomers using data from multiple telescopes measured a red hypergiant cataloged as UY Scuti. Their best estimates gave it a diameter of roughly 2.4 billion kilometers. Place UV Scuti where our sun currently sits. Its surface would expand outward, swallowing Mercury, then Venus, then Earth, then Mars, then continuing outward until it engulfed the orbit of Jupiter. The light reflected off a spacecraft sitting on UY Scuti's surface would take over 8 hours just to travel once around the star's circumference. 8 hours just to go around the outside of one star. And UY Scuti is just one star. One data point among an estimated 100 to 400 billion stars in the Milky Way alone. Most of those stars we have never seen individually. Most of them we will never name. They exist in numbers so large they lose meaning, and we have not left our own galaxy yet. This is where most scale videos stop. Earth to Jupiter to Sun to a giant star. The graphics are beautiful. The music swells. You feel appropriately small. But what comes next is where human intuition does not just struggle, it breaks, because the next step is not size. The next step is distance. And distance is a completely different kind of horror. Light travels at 299,790 kilometers per second. That sentence is worth sitting with for a moment. Not kilometers per hour, per second. In the time it takes you to blink, light has already traveled roughly 90,000 kilometers. In 1 second, it could circle the Earth 7.5 times. It is the fastest thing in the universe. Nothing we know of can exceed it. And it is not fast enough. This is the central problem of cosmic distance, the thing that breaks intuition more completely than any size comparison ever could. The universe is not just big in the way that a country is big, or even in the way that a planet is big. It is big in a way that makes even the speed of light seem inadequate. And to understand how inadequate, we start with the nearest star. Proxima Centauri sits approximately 4.24 light years from our sun. A light year is the distance light travels in 1 year, roughly 9.46 trillion kilometers. So Proxima is about 40 trillion kilometers away. If you scaled the solar system down so that the distance from Earth to the Sun was the width of a single grain of sand, about 1 millimeter, then Proxima Centauri would be another grain of sand, sitting roughly 600 kilometers away, not in the same room, not in the same city, 600 kilometers. Our fastest spacecraft, the Voyager 1 probe launched in 1977, is currently traveling at about 61,000 kilometers per hour. At that speed, it would take Voyager approximately 73,000 years to reach Proxima Centauri if it were headed in that direction, which it is not. 73,000 years to reach the nearest star, the nearest one. Now scale outward. The Milky Way galaxy is a flattened spiral containing somewhere between 100 and 400 billion stars, stretched across a diameter of roughly 100,000 light years. The solar system sits about 26,000 light years from the galactic center, on a minor arm called the Orion Arm. If you wanted to travel from one edge of the Milky Way to the other at the speed of light, the universal speed limit, you would spend 100,000 years in transit. Civilizations would rise and fall. The stars themselves would age visibly. Humanity has existed as a species for perhaps 300,000 years. The Milky Way is 1/3 of that wide. Your coffee is still in its cup. You are inside the Milky Way, moving through it at 8 to 28,000 kilometers per hour, and you will never cross it. No human will. Not even a signal moving at the speed of light sent today would reach the far edge of our own galaxy within a human lifetime. But the Milky Way is not alone. Our nearest large galactic neighbor is Andromeda, also known as M31. It sits approximately 2.537 million light-years away and contains roughly 1 trillion stars, more than twice the stellar population of the Milky Way. On a clear autumn night in the northern hemisphere, You can see it with the naked eye as a faint smudge near the constellation Perseus. That smudge is 1 trillion suns, 2.5 million light years away, and the light entering your eyes right now left Andromeda before Homo sapiens existed. You are looking 2.5 million years into the past. Andromeda is also heading directly toward us. At roughly 110 kilometers per second, the Andromeda galaxy is on a collision course with the Milky Way. In approximately 4.5 billion years, the two galaxies will begin to merge. Stars will not collide. They are too far apart for that. But the gravitational interaction will reshape both galaxies completely. What emerges from the merger will not look like either one. A new structure will form. Astronomers have given it the working name, Milkomeda. We're falling toward each other in slow motion across millions of light years, and we have been since before life existed on Earth. Together, the Milky Way, Andromeda, and about 50 smaller satellite galaxies form what astronomers call the local group. The local group spans roughly 10 million light years. For decades, this seemed like the relevant neighborhood, our cosmic zip code. But in 2014, a team led by astronomer Brent Tully at the University of Ohio published a paper that rewrote the map. They identified a structure they named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster of galaxies, and the local group is just a small piece of it. Laniakea contains over 100,000 galaxies. Its diameter is approximately 529 million light-years. Our entire local group, including the Milky Way and Andromeda, fits inside Laniakea the way a single grain of sand fits inside a football stadium, and Laniakea is being pulled toward something. That something is called the Great Attractor, the same mass concentration mentioned earlier that is dragging our galaxy at 600 kilometers per second. For decades, astronomers could not identify the Great Attractor because it sits in a region of sky that our own Milky Way's disk obscures. The plane of the galaxy was hiding it. When X-ray telescopes finally pierced through, what they found was a supercluster of galaxies called the Norma Cluster, sitting at the gravitational center of an even larger structure. We are falling toward it. We have always been falling toward it. We will never reach it in any meaningful time frame. We are falling towards something you spent decades unable to see. In a supercluster we did not know we belonged to. In a galaxy rushing toward another galaxy. In a universe that is, by any honest reckoning, doing everything it can to make you feel lost. And then there is the bootless void. In 1981, astronomers conducting a survey of galaxies in the northern sky noticed something strange. A region of space roughly 330 million light-years across appeared to contain almost nothing. No galaxies, no clusters, an enormous sphere of near emptiness in a universe that everywhere else seems packed with structure. The bootless void is not perfectly empty. Later surveys found a small number of galaxies scattered inside it, but it is vastly underdense compared to the cosmic average. If the Milky Way were located inside the bootless void, we would not have known other galaxies existed until the 1960s. The nearest galaxy would have been so far away that early telescopes would have missed it entirely. We would have looked out and seen only darkness, and we might have concluded we were alone. We would have been robbed, but we would have had no way to know it. That thought should settle somewhere uncomfortable. Now look in the opposite direction from the void. In the constellation boundary between Hercules and Corona Borealis, astronomers have identified what is currently considered the largest known structure in the observable universe. The Hercules Corona Borealis Great Wall is a filament of galaxies and galaxy clusters stretching approximately 10 billion light-years across. It is so large that it challenges certain cosmological models that predict the universe should be uniform at the largest scales. Its existence is, to put it plainly, a problem that cosmology is still working to explain. The universe contains structures whose existence we do not fully understand, and we found them by looking. The question is, what else is out there that we are not yet able to see? The answer to that question has a name. It is called the observable universe, and the word observable is doing far more work in that phrase than it appears to be. The observable universe is not the universe. That distinction matters enormously. When physicists and cosmologists use the term observable universe, they mean something precise. The spherical region of space from which light has had enough time to reach us since the Big Bang, approximately 13.8 billion years ago. If something is so far away that its light has not yet had time to reach us, we cannot see it. It is not in our observable universe, not because it does not exist, but because the universe has not given us long enough to receive its signal. Here is where it gets strange. You might expect the observable universe to have a radius of 13.8 billion light years, since that is how old the universe is. Light that has been traveling toward us for 13.8 billion years should be 13.8 billion light years away. But the observable universe has a radius of approximately 46.5 billion light years, a diameter of about 93 billion light years, nearly 7 times larger than simple arithmetic would suggest. The reason is expansion. Space itself is expanding. The objects that emitted the light we are now receiving were closer to us when they emitted it. But in the time that light spent traveling toward us, the space between us and those objects expanded. The objects are now much farther away than the light years traveled would imply. The light we receive today from the most distant observable objects was emitted from sources that are now roughly 46 billion light years from us, even though we are receiving light that has only traveled for 13.8 billion years. The universe is larger than the time it has existed would allow, because the universe is not sitting still, it is growing, and critically, it is not growing at a steady rate. It is accelerating. In 1998, 2 independent teams of astronomers studying Type Ia supernovae, a class of stellar explosion that can be used as a standard cosmic measuring stick, made a discovery that earned the Nobel Prize in Physics in 2011. The universe is not just expanding. The rate of expansion is increasing. Distant galaxies are not just moving away from us, they are accelerating away. Something is driving that acceleration. Physicists gave it a name, dark energy. What dark energy actually is, no one knows. It is not a cop-out or a placeholder. It is a genuine active mystery sitting at the center of cosmology. Current estimates suggest that dark energy makes up approximately 68% of the total energy content of the universe. Another 27% is dark matter, also not directly observed, inferred from gravitational effects. The ordinary matter you can see, touch, and measure. Stars, planets, gas, dust. You, your coffee cup, makes up roughly 5% of the universe, and 95% of everything is, in the most literal sense, unknown. The James Webb Space Telescope, launched in December 2021, has been challenging cosmological assumptions since it began returning data. Galaxies detected by Webb appear to be older, more massive, and more fully formed than models predicted for that era of the universe. The standard model of cosmic evolution, built over decades of meticulous observation, suggested that early galaxies should be small and chaotic, still assembling. What Webb is finding are large, structured, fully formed galaxies existing in an era where they should not yet be able to exist. We are in the middle of rewriting the map of the early universe in real time, with the telescope sitting 1.5 million kilometers from Earth, looking back 13 billion years. Now look at the largest scale. If you could zoom out far enough to see the observable universe as a single object, the way you might see the Earth from orbit, what would you see? Not a random scattering of galaxies, not uniform distribution. What you would see is the cosmic web, a vast filamentary structure in which galaxies cluster along thin threads and sheets separated by enormous empty voids. The filaments intersect at nodes where the densest galaxy clusters sit. The voids between them are the cosmic equivalents of the Botte's void, vast empty spaces that take up most of the universe's volume. The cosmic web looks, in satellite images and simulation renders, strikingly like the neural network of a brain. Filaments connecting nodes, voids in between. Information, or in this case, matter flowing along the threads. The resemblance is coincidental. It tells us more about the mathematics of network formation than about any deep connection between consciousness and cosmos. But it is striking. It is deeply, uncomfortably striking. Here is the question that tends to follow. What is beyond the observable universe? The honest answer is that we do not know and cannot know by definition. But physics allows us to reason about it. If the universe is infinite, which current evidence does not rule out, then beyond our observable bubble, there is simply more universe, more galaxies, more stars, more planets, exact copies of our cosmic web extending infinitely in all directions. Some cosmologists take this seriously enough to conclude that, given infinite space, every possible arrangement of matter must repeat, including, somewhere, an exact copy of Earth, an exact copy of you reading this. That is not mysticism. That is what infinity requires if the universe is truly infinite and the laws of physics hold uniformly throughout. Other models suggest our universe may be one of many, a multiverse of separate spacetimes, each with potentially different physical constants, different laws. In some of those universes, the constants that allow stars to form, planets to coalesce, and chemistry complex enough for life to emerge might not hold. In others, they might be even more hospitable. We have no evidence for any of this, but we have no way to rule it out either. The edge of the observable universe is not a wall, it is a horizon. It is the boundary of what we can currently see, not the boundary of what exists. Beyond it, the universe continues in ways we may never know, because the light from those regions will never reach us. The expansion of space will carry those sources beyond our horizon faster than their light can travel toward us. We are isolated, not by walls, but by speed. Not by emptiness, but by time. Come back to where we started. You are sitting on a rock. That rock is spinning. It is orbiting a nuclear furnace. That furnace is orbiting a galactic center. A galaxy is being pulled toward the great attractor. Your galaxy sits in a local group, in a supercluster called Laniakea. In the observable universe, in whatever exists beyond the observable universe, in an arrangement whose total extent we may never know. Your coffee is still in its cup. The human nervous system was not designed to feel galactic motion. It was not designed to comprehend 93 billion light years. It was designed to track prey across a savanna, to read the faces of roughly 150 people, to navigate a territory of a few dozen square kilometers. Every piece of cognitive equipment you use to process this information was built for a world smaller than a single light second. And yet here you are, doing it anyway. Here's what Brent Tully's discovery of Laniakea actually means. Here is what the James Webb Telescope looking back 13 billion years actually means. Here is what the cosmic web, the Boötes void, the Hercules Corona Borealis Great Wall, the acceleration of the universe actually means. It means that the universe has, through a chain of events, beginning with the Big Bang, produced a structure capable of measuring itself. You are made of atoms forged in the cores of stars that died billions of years before the sun formed. The calcium in your bones, the iron in your blood, the oxygen in your lungs, all of it built in stellar furnaces and scattered through the galaxy in supernova explosions across billions of years. You are not separate from the universe. You are the universe. You are its most recent and most improbable attempt to look back at itself and understand what it is. That is not poetry. That is physics. The disturbing reality of our true size in the universe is not that we are small. Small is just a measurement. The disturbing reality is this: we are temporary. The universe will continue long after every star has burned out, long after every black hole has evaporated through Hawking radiation in a time frame so vast it makes the current age of the universe look like a single heartbeat. On that time scale, everything you have ever known, every civilization, every species, every record of human thought will be indistinguishable from nothing. That right now in this cosmically brief window there are eyes, there is measurement, There's understanding. The universe has organized itself into something that notices it exists. That is not a small thing. That might be the only thing. If this video shifted something in how you see your position in the cosmos, share it with someone who needs the perspective. The next video in this series asks what happened in the first second after the Big Bang. A question whose answer is stranger than anything in this one. It is already waiting for you.